discuss transformation of matrices, or elementary row or column operation. A matrix can be transferred into another matrix by changing its rows or columns through some elementary operations, okay, which are given below. First, we interchange of any rows or columns. We interchange any rows or columns. That means we interchange first row with second row, first row with third row. Similarly, we interchange any columns, first column with the second column with the third column, etc. Second point, multiplying the elements of a row or a column by a non-zero scalar. We multiply the elements of a row, all the elements of a row or column by a non-zero scalar. That means, suppose Ri is the row of ith row element. We multiply the scalar Kri. So similarly, if we multiply the ith column with the scalar k, then we write Ci represent KCi. That means we multiply any row or any column of a matrix with a non-zero scalar. Okay. Third, replacing a row or column by adding to it a non-zero scalar multiples of elements of another row or column. That means we replace, suppose first row element represented as the first row element plus k times of a second row element, or second row element represented the second row element plus k times of a third row element. Symbolically, we write Ri represent Ri plus k Rj. If we write first row element, then we write R1 represent R1 plus k R2, etc. Okay. So now we take an example about this representation, that a transform now we take an example transform the matrix 6 3 2 2 into unit matrix. Okay, that we transfer the matrix into unit matrix of a second order 1 0 0 1. Now this matrix is 6 3 2 2. So if we multiply 1 by 3 in the first row, multiply 1 by 3 in the first row, 1 by 2 in the second row. That means we divide the first row element with 3 and second row element with 2. Then we write here R1 represent 1 by 3 R1, R2 represent 1 by 2 R2, 1 by 2 R2. So finally we get a matrix of 2 1 1 1, 2 1 1 1. Then we transform it to a unit matrix. So we subtract first row element from second row, that means R1 represent R1 minus R2, R1 represent R1 minus R2, minus R2. So we get a matrix 1, 2 minus 1, 1, 1 minus 1, 0, 1, 1. Okay. Next, we transform R2 second row element represent R2 represent R2 minus R1, R2 minus R1. R2 minus R1. So we get a 1, 0, 0, 1, which is an identity matrix or unit matrix. Okay. Now, using this transformation, we find the inverse of a matrix. Using this transformation of a matrices, we find the inverse of a matrices. Last class we discussed inverse of a matrices using cofactor adjoint. Here we find a inverse of a matrices using elementary row operations or column operations. Okay, we find the inverse of a matrix using elementary row operation or elementary column operation. First, we discuss elementary row operations. Elementary row operations. Okay. Let capital A is a square matrix of order n. N means maybe 2, 3 or 4, etc. You have a highest power 3. Let A is a square matrix of order n, and capital I is the unit matrix of the same order. Unit matrix of the same order. Okay. Suppose capital A is invertible. Okay. A is invertible. Now we find A to the power minus 1 or A inverse. Okay, we write capital A as A is equal to IA. You know, I is the unit matrix, A is a square matrix, of order n, I is the unit matrix of the same order. Okay. Transform. Now we transform the matrix involved in such a manner okay. First step, the post factor on the right, IA, pre-factor I, post factor A. The post factor A in the RHS is left unchanged or remains unchanged. The post factor capital A in RHS right hand side is left unchanged. Number 2, capital A in LHS gets transformed into unit matrix. Transformed into unit matrix through the row operations which are to be reflected in the prefactor I in the RHS. Number 2, the matrix A, capital A in LHS gets transformed into unit matrix transformed into unit matrix I through row operations which are to be reflected onto the prefactor capital I in RHS. Okay, that means the matrix A in the LHS get transformed into a unity matrix that row using row operations that should be maintained on the prefactor I on the right hand side. Okay, so it becomes I is equal to BA. That means the unit matrix I becomes a new matrix B. Okay, since we have supposed capital A is invertible. Suppose capital A is invertible. A inverse exists such that A into A inverse that equal to A inverse into A equal to I. A into A inverse into A equal to I. So B is equal to A inverse. So B is equal to A inverse. Okay. Similarly, we discuss elementary column operations. Generally, we do the problem using elementary row operations. Elementary row operations. Okay. Elementary column operations. Elementary column operations. We write capital A as A is equal to AI. Similarly, on the RHS of A remains unchanged. The matrix capital A on RHS remains unchanged. Carry out to elementary column operation. Carry out elementary column operations. On capital A on LHS until we convert it to until we convert it to a unit matrix. Okay. Simultaneously applying the same column operations. Simultaneously applying the same column operations on capital I on RHS. So we get I is equal to AB, that implies B is equal to A inverse. Okay. Now we discuss an example using row operations. Find the inverse of a matrix. Example from your exercise 4B number 11. Find the question is find the inverse of the matrix 1 2 I 1 2 3 5 using elementary row or column operations. Okay, let capital A equal to 1 2 3 5. We know that we write the A as IA, A. That imply 1 2 3 5 is equal to 1 0 0 1. That A remains unchanged, so we write it as A. Now we do it using elementary row operations. So we change this matrix 1 2 3 4 as a unit matrix. So R2, first transform the R2 minus 3R1. So 1 2 R2 minus 3R1. 3 minus 3 into 1, that equal to 0. 5 minus 3 into 2, that means 6. 5 minus 6 minus 1. 5 minus 6 minus 1. Same operation on the unit matrix, so we write 1 0, that is 0 minus 3R1, that means minus 3. 1 minus 3R30, that will equal to 1. That is 1 remains unseen. That implies now 1 0, similarly 1 0 0 1. That is R1 represent R1 plus 2R2. R1 plus 2R2. So we write here 1 plus 0 in 2 into 0. That means 0. 1 plus 0 0. 1 plus 0 1 plus 0 1. That we write here. Similarly 2 plus 2 into minus 1. That equal to 0. 0 minus 1. That equal to 1 plus 2 into minus 3. That is minus 6. That is 1 minus 6 minus 5. Similarly 0 plus 2 into 1. That equal to 2. Here minus 3 1 whole into A. Okay. Now we represent R2 as minus 1 whole into R2. So 1 0 0 1, that equal to minus 5 2 3 minus 1 whole into A. So here A inverse equal to minus 5 2 3 minus 1. Okay, minus 5 2 3 minus 1. Okay, now take another example. inverse of a matrix using row operation, that is third order matrix from your exercise. And the inverse of a matrix, exercise 4b number 12b. Important question in the last year 2019 in CHC. So you find the inverse of the matrix 1 2 1 2 3 2 1 4 1 0 2. Okay, using elementary transformation. Transformations means elementary row operation or column operation. Now we write, let capital A is equal to 1 2 3 2 1 4 1 0 2. We find the inverse of A using row operations. Now we write capital A as A is equal to IA, that equal to 1 2 3 2 1 4 1 0 2 1 0 0 0 1 0 0 0 1, that is A. Okay, now we transform the second row element R2 represent R2 minus 2 R1, R3 represent R3 minus R1, R3 minus R1. That implies, here we write 1 2 3 R2 minus 2 R1, that means here 0, 1 minus 4 minus 3, 4 minus 6 minus 2. Similarly here R3 minus R1, that thing should be written on the right hand side unit matrix. 1 0 0 at 0 minus 2, that means minus 2, 1 minus 0 1, 0 minus 0 0. R3 minus R1, 1 minus 1 0, 0 minus 2 minus 2, 2 minus 3 minus 1, 0 minus 1 minus 1, 0 minus 0 0, 1 minus 0 1. Okay, now we transform the first row element as R1 represent 3R1, R3 represent 3R3, R3 represent 3R3. That means we multiply each element of first row with 3 and third row with 3. So the matrix becomes 3 6 9 0 minus 3 minus 2 0 minus 6 minus 3 0 minus 6 minus 3. Similarly, here the unit matrix becomes 3 0 0 minus 2 1 0 minus 3 0 3. That is A. That equal to A. Okay. Now we transform that the first row element minus 5 times of third row element. That implies first row element R1 minus 5 R3 and R2 represent R2 plus 2R3. Okay. Here R1 represent R1 minus 5 times R3. 5 times R3. R1 minus 5 times R3. Okay. Sorry. That R1 represent R1 plus 2R2. 2R2. R1 represent R1 plus 2R2. R3 represent R3 minus 3R2. R3 minus 2R2. So here we get 3 R1 plus 2R2. 3 here 0 6 plus 6 9 plus 2R2. That means 5. Here 5. Same thing maintained on the right hand side unit matrix. So here we write 3 plus 2R2. That means 3 minus 4 minus 1 2 0. Okay. That is R3 represent R3 minus 2R2. R3 minus 2R2. R3 represent here 0 minus 3 minus 2. Here minus 2 1 0. Minus 2 1 0. R3 minus 2R2. R3 minus 2R2. Here 0 0 2R2. 0 minus 6 plus 6 0 minus 3 plus 4 minus 3 plus 4 1. Okay. Here 0 minus 1 minus 2 3. 1 minus 2 3. Okay. Now that implies here we write R1 represent R1 minus 5 R3. R2 represent R2 plus 2R3. R2 plus 2R3. So here 3 minus 0 3 0 minus 0 0 5 minus 5 5 times R1 minus 5 R3. So 5 minus 5, 0. Similarly, R2 plus 2, R3, 0, minus 3, 0, 0, 0, 0, 1. Same condition, minus 1, 2, 0, minus 1, R1 minus 5 R3, R1 minus 5 R3 means minus 6, 12, minus 15. Minus 15, that second row becomes 0, 0, minus 3, 6, 0, minus 3, 6. 0 minus 3, 0, 0, sorry, 0 minus 3, 0, R2 plus 2 R3, R2 plus 2 R3, R2 plus, R2 represent 0 plus 6, 6, 6, here 6. That equal to that my 1 minus 2, 3. Okay. Last, if we multiply R1 1 by 3 R1 R2 minus 1 by 3 R2. So that this matrix becomes 1, 0, 0, 0, 1, 0, 0, 0, 1. That equal to, that becomes minus 2, 4, minus 5, 0, 1, minus 2, 1, minus 2, 3, A. So A inverse, that imply A inverse is equal to minus 2, 4, minus 5, 0, 1, minus 2, 1, minus 2, 3. Okay. Thank you.